Alright, y'all, type 7. And as you can see, my creativity juices are flowing. Type 7 is a tricky one, so I said we got a pickle. But I know in Portuguese, y'all instead say we have a pineapple, so I've included both. Multicultural we are. We can also say that I am up the creek without a paddle. That means you're stuck. But I'm going to give you the tools today so that you don't have to dive into the water to get your paddle. You've got the tools in your boat to paddle away to the shores of the correct solution. Oh man, I'm on top of it. On point. All right, here's example 1. I'm going to do example 2 as well, but after we do example 1, again, you should try it on your own before we move on. First step, ask yourself, can you combine like terms? If the answer is yes, then go ahead and isolate that trig expression. However, we've got cosine and sine. Those are two different trig expressions, so we cannot combine them. So the answer is no. So then we've got to ask ourselves again, do we have different trig expressions or do we have different exponents? Same trig expression but different exponents. If just the exponents are different, then we can go the factoring route. That's what we were just doing, where you get it equal to 0, write it in standard form from highest exponent to lowest exponent, check for GCF, and then factor. We find two numbers that multiply to be the first and the last and add to be the middle. So we've all mastered this. But we can see in this case that we don't have different exponents. We have different trig expressions. We have cosine and a sine. So instead, we're going to go the identity route. So first we want to try to use an identity to make all the trig expressions the same. The only trig expression that involves cosine and sine is when cosine and sine are squared, and neither one of these are squared. So I'm going to make it squared. I'm going to force an identity into this equation by squaring both sides. All right, so there's step 1. We're going to square both sides. Be super careful here that when you square this, this doesn't become cosine squared plus 1. We have to distribute, okay? So we're going to distribute that out. I'm going to have cosine of x plus 1 times cosine of x plus 1. And then over here, I just have plain old sine squared, okay? Cosine x times cosine x is cosine squared x. Cosine x times 1 is cosine of x. Cosine of x times 1 is cosine of x, and 1 times 1 is 1. And we still got sine squared. Combine your like terms. Cosine x and cosine x are like terms because they are the same trig expression and have the same exponent. Now when I combine like terms, keep in mind that we only add the coefficients together. So 1 plus 1 gives us 2 cosine of x plus 1. Cosine squared stays the same because there's no other cosine squareds, and 1 stays the same because there's no other constants. Equals sine squared. All right, so now we can use our identity. We have sine squared. So now we can use that identity that is sine squared of x plus cosine squared of x is equal to 1, right? I want to replace sine squared. I mean, I could replace cosine squared, but since I have this plain cosine here, that wouldn't help me too much. So I'm going to instead replace the sine squared. So sine squared is equal to 1 minus cosine squared. So I'm going to replace this sine squared with 1 minus cosine squared. Everything else stays the same. Cosine squared of x plus 2 cosine of x plus 1 is equal to all that. Okay, now my answer to this question is that I just have the same trig expression but different exponents. So now I can follow this route. We're going to get it equal to 0. So I need to pass everything to be on the same side. We're going to get it equal to 0 is our first step. So I'm going to do plus cosine squared. Cosine squared plus cosine squared will give me 2 cosine squared of x. There's no other cosine, so I just have plus 2 cosine of x. And then when I do minus 1, 1 minus 1 will cancel and give me 0. So they'll cancel out. All right. Then write in standard form, already squared and then to the first power, so it's already highest exponent to lowest exponent. Check for a GCF. They both have 2 in common and they both have cosine in common. So I'm going to divide that out. So I'm going to have 2 cosine of x If I divide this term by 2 cosine x, I'll be left with just cosine x. 2 cosine x divided by 2 cosine x is 1. Okay? Now I've got two factors equal to 0. They multiply to be 0, so I can set each factor equal to 0. So I've got 2 cosine of x is equal to 0, and cosine of x plus 1 is equal to 0. Over here, divide by 2, 0 divided by 2 is 0, so cosine of x can be equal to 0, or cosine of x can be equal to -1. Now we're not done. The goal is to solve for x, right? And my x has to be between 0 and 2 pi. We can be equal to 0. We cannot be equal to 2 pi. Remember, the brackets means that we're including. The parentheses means we are not including. So where is cosine equal to 0? Remember, cosine is our x value, so where on our x-axis are we 0? That would be when we are on our y-axis. So at pi over 2 and 3 pi over 2. Okay? And then cosine is -1 when we are -1 on our x-axis, so x is equal to pi. Okay? Now, you may think that we are done, but let's look back at our list. So we used an identity to make all the trig expressions the same. By forcing an identity, we squared both sides. Now, whenever you square both sides, we have these two caveats here. We need to separate the trig expressions. Now, up here, they were already separated, but if I had cosine and sine on the same side, I would need to pass it to the other side. I need to have just one trig expression on each side of my equation, or else things are going to get real messy, and we don't want that, okay? The other thing is we need to check for extraneous solutions. Anytime you square your equation, you are running the risk of inserting false solutions, extraneous solutions into your solution set. So we need to check all of them to make sure that they are actually correct. So into my original black equation, ignoring the orange bits, we're going to plug in these values. So x equals pi over 2. We're going to check it. And remember, we're plugging it into cosine of x plus 1 is equal to sine of x. Okay? If we plug that in, we've got cosine of pi over 2 plus 1 is equal to sine of pi over 2. Well, cosine at pi over 2 is 0 plus 1, and sine of pi over 2 is 1. 0 plus 1 is 1, so that is true. So this is an actual solution, okay? Pi over 2 works. Let's see if 3 pi over 2 works. So x equals 3 pi over 2. We're going to plug it in. Cosine of 3 pi over 2 plus 1 is equal to sine of 3 pi over 2. All right, cosine of 3 pi over 2, that puts us down here. That is 0, right, because we're on our x-axis. So cosine is 0 at 3 pi over 2. Plus 1. Now sine at 3 pi over 2 is -1. We're going in the negative direction on our y-axis. Now positive 1 is not equal to -1. So this is a false solution. This one does not work. So I'm just not going to box it in. I'm not going to box it in over here either. I'm only going to box in the final actual solutions, which is not 3 pi over 2. Lastly, we're going to check x equals pi. So x equals pi. Plug it in, cosine of pi plus 1 is equal to sine of pi. Y'all getting hungry with all the pi? Cosine of pi is -1. We're going -1 on our x-axis, plus 1. And sine of pi, since we're not moving along our y-axis, sine of pi would be 0. -1 plus 1 is 0. That is indeed equal to 0. So that is a true, valid solution. Okay? So whenever you square both sides, anytime you square both sides, you've got to check for extraneous solutions. You've got to plug it back in to make sure you did it all correct. Now, I'm going to do the second example as well, but I strongly encourage you to try it on your own. The reason I'm going to do it is because there are two different ways of doing it, and you might do it either way. So I'm going to show you both ways so that you know, but try it on your own first. Struggle by yourself first. It's always the healthier option.